Hello. Hello, Nyan. This is your hacker nickel wife Cyan. Welcome, everyone. Welcome to it. Welcome, Paul. Welcome, Jan. Welcome, user 670. Meow. Welcome, Batomi. Welcome, Lloyd. Welcome, Mohammed. Hello. Hello. Today, we're learning functional language features, iterators, and closures in Rust. It's fun stuff. It's functional programming. Everybody loves functional programming, and today we're going to do some stuff. Yosh. Okay, let's go. Rust design has taken inspiration from many existing languages and techniques, and one significant influence is functional programming. Programming in a functional style often includes using functions as values by passing them in arguments, returning them for other functions, and assigning them to variables for later execution, and so forth. Honestly, the first time I saw people pass function as an argument, it was shocking. It was a life-changing experience when they take an argument as a function or return a function. Oh, I'm so sorry for light mode. I'm gonna change it now. すみません. Okay. So we're going to cover closures and iterators. Closure is a function-like construct you can use to store in a variable. So basically you store a function-like construct in a variable. And we'll talk about iterators, a way of processing a series of elements. I don't know if we'll improve the IO project thing. We might. I think we did finish the IO project last time. So we might do it. And they're going to talk about the performance of the two features. They're faster than we might think. What is overrated? Light theme? Or functional language? Other Rust features such as pattern matching and enums, which we have covered in the other chapters, are influenced by the functional style as well. Mastering closures and iterators is an important part of writing idiomatic fast Rust code. So let's devote this entire chapter to them. Okay, what are we going to have? Closure, anomalous function that can capture their environment. Rust closures are anomalous functions you can save in a variable or pass as argument to other functions. So it doesn't have a name, it's anomalous. And you can save them into variable and pass as argument to other functions and return from function. You can create closure in one place and then call closure to evaluate it in a different context. Unlike functions, closures can capture values from the scope in which they are defined. We'll demonstrate how these closure features allow for code reviews and behavior customization. Function as argument is not a rare in MATLAB. Oh, that I didn't know. I only remember using MATLAB doing math stuff. I think the index began from 1, which is a little weird compared to other languages. Welcome, Nerden! And welcome, Bike Dream. Creating an abstraction of behavior with closures. Let's work on an example of a situation in which it's useful to store a closure to be executed later. Along the way, we'll talk about the syntax of closures, type inference, and traits. Consider this hypothetical situation. We work at a startup that's making an app to generate custom exercise workout plans. The backend is written in Rust, an algorithm that generates the workout plan takes into account many factors, such as app's user page, body body mass index, exercise preference, recent workouts, and an intensity number they specify. Okay, it takes some arguments, age, body mass, BMI, exercise preference, recent workouts, and intensity number. The actual algorithm used isn't important in this example. What's important is this calculation takes a few seconds. Oh, so this calculation is costly in time. We want to call this algorithm only when we need to, and only call it once, so we don't make the user wait more than necessary. We'll simulate calling this hypothetical algorithm with the function simulated expensive calculation, which will print calculating slowly, wait for 2 seconds, and return whatever the number we pass in. So this is like a function that returns the calculation, the result of the calculation, and is quite slow. Okay? So next is the main function, which contains the parts of the workout app important for this example. This function represents the code that the app will call when a user asks for a workout plan. Because the interaction with the app frontend isn't relevant to the use of the closures, we'll hardcode values representing inputs into our program and print the outputs. The required inputs are this: an intensity number from the user, which is specified when they request a workout to indicate whether they want low intensity workout or high intensity workout. A random number that generates some variety in the workout plans. The output will be recommended workout plan. Okay, so we are going to write a main function that outputs a recommended workout plan. Generating workout. We've hard-coded the variable simulated user-specified value as 10. Okay, so we have this hard-coded value, user-specified 10, and we have a random net value of 7. And then we put them into this generated workout. And it's supposed to calculate the workout intensity. It's a smart, quote-unquote smart AI program. Supposedly. Now we have the context. Let's go through the algorithm. The function generate workout contains the business logic of the app that we are most concerned with in this example. The rest of the code changes in this example will be made to this function. Okay, so we have a bunch of code that generated workout, given an intensity number and a random number. So if the intensity is less than 25, it's gonna calculate how many push-ups it's gonna do. And do this twice, looks like. And if a random number equals to 3, it'll take a break. If it's not equal to 3, it'll say run for so many minutes. The code has multiple calls to a slow calculation function, so it has called the same calculating function for 3 times. So it's gonna be really slow. The desired behavior of generate workout function is to first check whether the user wants low intensity workout or high intensity workout. But this is the low intensity workout and this is the high intensity workout. And low intensity workout has push-ups and sit-ups. Oh, it's push-up and sit-ups. And for the high intensity, it has run. And if it's high intensity and that random number happens to be 3, then the app will recommend a break and hydration. So there's break for high intensity workout, but not for low intensity workout. It's weird. This code works the way the business wants it to now, but let's say the data science team decides that we need to make some changes to the way we call the simulated expensive calculation function in the future. To simplify the update when those changes happen, we want to refactor this code so it calls simulated expensive calculation function only once. We also want to cut the place where we're currently unnecessarily calling the function twice, without adding any other calls to that function in the process. That is, we don't want to call it if the result isn't needed, and we still want to call it only once. So we want to call this function only once. So they are refactoring this function by using a variable to store the result of the calculation. And then it used the same result for all 3 times. This change unifies all the calls to simulate expensive calculation and solves the problem of the first if block unnecessarily calling the function twice. Unfortunately, we're not calling this function and waiting for a result in all cases, which includes the inner if block that doesn't use the result value at all. What does it mean? With unify, I thought it stored the result into the expensive result. Oh, so the point is in this block, it doesn't really need the result, but we still calculate for it. So it falls into this random block. In this block, we unnecessarily calculate the result. And looks like we only want to calculate result for the blocks that actually need to. So how did we do that? We haven't done anything related to closure yet. Looks like. So now we can use closure. Let me take the code from here. This is all the code so far. And as you can see, it's zooming a little. But as we can see, the expensive result has been calculated for all the cases. That's the line that's in here. And we are going to refactor the code with closure. So the function will be called only when necessary. So we'll let the expensive closure be a closure. Put the variable inside this straight lines. And then we print line. Oh, those are exactly the content of the function above, so I just copy them and format. Sorry, the OBS was a little messed up. But it's back. Looks like my internet is okay today. You're cute. Thank you. Thank you, Jen. So I'm doing her own AI now? Not yet. We're far from there. We're still in the 1970s. I'm coding an assistant like Cortana Siri. When? How do you code it? How do you do a voice assistant? I need to have some like voice input. That'd be fun. That would be a fun idea actually. I should do one. Is it live from a few days ago? Yeah, it is live. Hello, welcome. I'm just kind of focused. It's pre-recorded live from a couple days ago. We're all paid actors. Yeah, you guys. We have aligned the chat. We have about 1,000, not 1,000, about 20 YouTube accounts to post the message at exactly the same time we wanted to send. The chat is only launching. Hi, I'm alive too. I demand a race. No race. Come strike at me. Okay, coming back to this function. The print line is sleep, and then we return the number I was putting. Look, isn't this gorgeous? We successfully put the entire function into a variable. A function is equals to a variable, and a variable is equals to a function. And that's amazing. Stop outstopping, yo! Upcom. Pivot. Okay, we have our expensive closure. How are we going to use it? So whenever we use it, we pass in an intensity. So look, we're using this closure, and we're using this but taking an intensity number. And here, for the same thing, I put that random number, and it's going to return the same number. And same thing for here. Okay. Okay. We have used our closure. Let's see if this runs. A little syntax error. Line 27. Are we using a bracket? Is it good now? Okay, it's slowly calculating. So the random number equals to 7. The intensity equals to 10. So it goes into this case, saying today do 10 push-ups, and next do 10 sit-ups. Generate workout. I still had an idea for such a program. It ended up with chocolate pudding. Maybe it's like eating celery. The amount of energy you use to eat and digest a chocolate pudding might be more than eating one. The calories the pudding actually has. Maybe it's the so-called 0 calories food. That's possible. So yes, we have created a closure and then used it in our functions. But while for this block, if the random number equals to 7, if it equals to 3, so the random number we set to 3. And for intensity we set it to 30. And then we run it again. And boom! It's going to give us the output immediately. Without calculating this closure. But the problem is, in this block, it's calculating it twice. We could fix this problem by creating a variable local to that if block to hold the result of calling the closure. But closure provides us with another solution. We'll talk about that solution in a bit. But first, talk about why on-type annotation in the closure definition and the traits we involve with closure. So we'll come back to this program. Are we? Morning, welcome. While she writes a workout program, I'm ordering ice cream. Why did you order ice cream? Does ice cream have takeouts? Did fancy people order ice cream to deliver? That's so cool. I always just take them from the fridge. Okay, closure type inference and annotation. Closures don't require you to annotate the types of parameter or a return value like functions do. Type annotations are required on functions because they are part of explicit interface exposed to your users. Defining this interface rigidly is important for ensuring that everyone agrees on what types of value a function uses and returns. But closures aren't used in exposed interface like this. They are stored in variables and used without naming them and exposing them to user of our library. So for functions, we need to specify the type. But for closures, we don't really need to. It's not enforced to declare a type for the closure. Closures are usually short and relevant only within a narrow context, rather than in any arbitrary scenario. With this limited context, the compiler is reliably able to infer the types of the parameters and return type, similar to how it is able to infer the types of the most values. So it's saying that the compiler will be able to infer the types. Both the return type and the argument type. Making programmers annotate types in this small anonymous function will be annoying and largely redundant with the information the compiler already has available. As with variables, we can add type annotation if we want to increase explicitness and clarity at the cost of being more verbose than is strictly necessary. Annotating the types for the closure we defined would look like the definition shown here. So if we were to annotate it, I will actually write it and write the type of the output. But we don't need to. With the type annotation added, the syntax of closure looks more similar to the syntax of functions. The following is a vertical comparison of the syntax for a definition of a function that adds 1 to its parameter and a closure that has the same behavior. We've added some space to line up the relevant parts. So here. This function have an input and an output, and we plus 1 to the value. And then this is a closure that has type annotation. And this is the closure that doesn't have type annotation. And this is a closure that doesn't even have the curly braces. The first line shows a function definition, and the second line shows a fully annotated closure function. And fourth line shows removes the brackets, which are optional because the closure body has only one expression. If we line it up, we realize if we could write a function like this instead of this or that, it's a lot more simpler. It's a lot simpler. Calling the closure is required for add1 v3 and add1 v4 to be able to compile, because the types will be inferred from their usage. So in the usage time, the compiler will infer the type of the input and output. So if there is no usage for those, then I bet the compiler won't compile, because it won't let a closure that doesn't have the correct type to compile. Closure definitions will have one concrete type inferred for each of their parameters and for their return type. For instance, this shows the definition of a short closure that just returns the value it receives as a parameter. This closure isn't very useful, except for the purpose of this example. Note that we haven't added any type annotation to the definition. If we then try to call the closure twice, using a string as an argument for the first time and an integer the second time, we'll get an error. For this example, let me see if I can comment this and show this example. I always talk like a baby. Your grandma Cyan is going to get mad. I don't talk like a baby. Okay, what do we have here? So we have a closure that just returns a string that passed in. And first, we take a string, we pass a string in it. Actually, for this closure, it takes something and returns the same type of the same thing. So when we call it for the first time with a string, it's gonna work. Is that how I format this? I actually don't need to format it, right? And semicolon. This should work. This should just say hello. But if I add this line that calls this function with an integer 5, it's not going to compile, because the compiler already infer the type of the function to be a string instead of an integer. So if I run it, it wouldn't work. It needs to be a string. Lingo Mini. What is Lingo Mini? Do Do we have a crew of Ringo's friend here? Okay, that's that example. Storing closures using generic parameters and the function traits. Let's return to our workout generation app. Okay, so let me clear all of that. Returning to this amazing AI workout app that doesn't produce ice cream. This example is so healthy. It asks you to exercise instead of eating. Eating is healthy too. Let's return to our workout generation app. Okay, so our code was calling expensive calculation closure more times than it needs to. One option to solve this issue is to save the result of the expensive closure in a variable for reuse and use the variable in each place we need a result, instead of calling the closure again. However, this method would result in a lot of repeat code. Fortunately, another solution is available to us. We can create a struct that will hold the closure and the resulting value of the calling closure. So we can create a struct that cache the value we have calculated to be used later. The struct will execute the closure only if we need the resulting value, and it will cache the resulting value so the rest of our code doesn't have to be responsible for saving and reusing the result. You may know this pattern as memorization or lazy evaluation. Memorization or lazy evaluation. I think cache is a common interview question. What is it? LSU cache? I didn't know the concept of cache was important until I got into the algorithm. So the commonly accessed values will be stored on the layer that's closest to be used. So it's more efficient to retrieve their values. I think there's like a locality loss of like memories and stuff. It's described as like a long-term memory that's not frequently accessed is stored further away from the memories that are most oftenly accessed. So it's efficient to take it out. Yes. The function traits provided by the standard library. The function traits are provided by the standard library. All closures implement at least one trait. Function mute, or func once. What is this? What are those? What's func mute and func once? What is func once? The version of the call operator that takes by value receiver. What is func mute? The version of call operator that takes a mutable receiver. Is she asking us? I'm trying to figure out. I'm figuring things out as I go. So I'm reading the doc. And if you guys know, if you guys want to talk, there are traits representing objects that are callable. Func once is for object callable only once, which is ensured by consuming self. Oh, it consumes the self. That means if I call it a second time, it wouldn't work? So, if an instance... The instance of fun once can be only called once. It has closure that might consume captured variables. And fun mute can be called repeatedly and may mutate state. It takes a mutable receiver. Any instance of fun mute can be used when a fun once is expected. So fun once is a super trait of fun mute. And when you need a fun once, you can give a fun mute. Welcome Cecilia. Welcome Gula. Hello. Hello. Fun mute can be called multiple times and allows mutating captured data, but can only be called one at a time. Oh. Fun is the same as fun mute, but can also be mutably access the captured data, and can be called multiple times at once. They have the same semantics as regular ownership and borrowing. I've never heard of this in other languages. Have I? Calling immutably capturing closure. This squares the X. Oh. Okay. So you change it up. It takes the square of X, and this function do twice takes a mutable function of F. Funk. That X equals to 1. Add 2 to X is this. Do twice, add 2 to X. The do twice takes add 2 to X and call it twice. The 1 becomes plus 2 and it becomes 5. Oh. Oh yeah, that's fun to know. We add types to the function trait bound to represent the types of the parameters, and return values. The closure must have to match this trait bound. In this case, our closure has a parameter of type 32, unsigned 32, and returns an unsigned 32. So the trait bound we specify is that. Oh, so this is the type of the trait. So we are creating a struct of cashier. And it has a calculation of type T and value of optional unsigned 32. They are needed because closures are structs generated by the compiler, and their sizes may differ from one another because of captured data. The traits are used to refer them in a unified way. Closures are structs generated by the compiler. Wait, closures are structs? I'm confused. Internally, they're structs. Oh gosh. Oh gosh. I didn't know that. You can imagine them as structs with core method. Oh, that makes a little more sense. Thank you for subscribing, Itzy. Hello. Welcome to Youngstar. So here, we're defining a cacher that caches a value. The cacher struct has a calculation field of the generic type T. The trait bounds on T specify that it's a closure by using the function trait. So this is a closure, indicated by this. Any closure we want to store in the calculation field must have one unsigned integer 32 parameter and must return an unsigned 32 integer. So this closure of type T must take an integer and returns an integer. It can be nothing else. Functions can implement all three of the function traits too. If what we want to do doesn't require capturing a value from the environment, we can use a function rather than a closure where we need something that implements a function trait. The value field is of type options unsigned 32. Before we execute the closure, value will be null. When we run code using a cacher, ask for the result of the closure. The cacher will execute the closure at that time and store the result within a sum variant in the value field. Then, if the code asks for the result of the closure again, instead of executing the closure again, the cacher will return the result held in some variant. So before we execute the closure, the value will be null. When the code using a cache asks for the result of the closure, the cacher will execute the closure at that time and store the result with a sum variant in the value field. So when cacher executes the closure, it will store a sum variant in the value field. Then if the code asks for the result of the closure again, instead of executing the closure again, the cacher will return the result holding the sum variant. The logic around the value field we've just described is in here. So we can initialize a cacher with a closure and a value of none. And we have a value. We have value function. When the value function is called, it either return the value of the sum variant or calculate the value. Store the sum variant in the value and return the value. Oh, this is nice. This is how you do a cacher. This is how you cache stuff. We want the cacher to manage the struct field values, then letting the calling code potentially change the values in the field directly. So these fields are private. So those two are private. The new function takes a generic parameter t, which we have defined as having the same trait bound as the cacher struct. Then the new returns a cacher instance. This is being returned that holds the closure specified in the calculation field and a non-value in the value field, because we haven't executed closure yet. When the calling column is the result of evaluating the closure, instead of calling the closure directly, it will call the value method. The value is for the evaluation. It will return the value in self.value if it has some value, or calculate some value if it doesn't, and store it into the value. Let's do it. I'm streaming using the Windows and SSH into a Ubuntu machine. Oh, okay, let's do the struct. A struct of cacher and we need to specify the type. It's lowercase. It's a reuse32 big function to unsigned integer 32. Calculation is a closure, and value is not now. It's an option of unsigned 32. Okay, that is our cacher. And then the implementation. Intimate T, Cashier T, where T is of type this to 32. And then we're going to have two functions, two private functions. The first one is new, and then it takes in a calculation of type T, and then it returns a new cashier. And what do you have? What do we do in the new function? We return a cashier. Oh, it did it for me. So the calculation is just gonna be calculation. And the value is initialized till now. And here we return a cashier. We return a new cashier. Oh yeah. And yeah, this is not needed. That's the new function. That's when we initialize a cashier. And here is a function we put a value, or we return the value. We are going to change the value of self, and we're going to have an argument of type unsigned integer, and it's going to return a unsigned integer. And we're going to match the fancy if statement. We look at our current self.value. If self.value is sum, we're going to return that value. If self.value is null, we're going to calculate that value. That v equals to self.calculation argument self.value equals to v and then we return the v. Welcome back, son. Good afternoon. Hello, Juan. Yuan. Welcome. Hello, bro. What's up? Oh, it needs to be a optional of value. So yeah. So we have our value. We have our little cashier ready for our use. So we're going to use it in our generate workout. So are we still going to keep this? I think so. It's just that we will initialize our cashier with it. So we keep the content of the closure. And we call cashier new here. So instead of expensive closure, this is a expensive cashier. But if it's called the expensive result, I'll just call it expensive result. Oh. And here, expense, we use the value function. And I believe it takes intensity. And complete the print line. Same thing here. But it doesn't need to calculate the intensity twice. Calculate the result twice. It's going to use the internal cacher to reduce the number of calculations. How is Cyan doing? I'm just still following the tutorial. Nothing can go wrong. Nothing can go wrong. And same thing here. Wait. Hello, Chris. Welcome. Oh. Okay, what trouble do we have? Oh, it needs to be mutable. Mutable. Okay, let's see if this runs. Toggle run. Oh. I happen to go to the exception. Not the exception. I happen to go to the one that doesn't require calculation. Here. Now it will go to this else because it's larger than 25, and you will calculate the result once. Takes 2 seconds to calculate. Run for 30 minutes. That's a big run. And if I change the intensity to 20. Oh yes, to 20. It's going to use our cacher and its value. Yep. The value is gonna be the same. Is it gonna be exactly the same? Oh yeah, it's gonna be exactly the same. But since we have the cacher, it doesn't need to wait. It's much quicker than before. It does one run of calculation, and then both of the result just comes out. So we are saving some time. Efficiency is big. We learned something. Nothing can go wrong is exactly what you say before something go wrong. Oh my god. Have you guys seen a Netflix movie? I think there's like a Windows XP pun, not a pun, joke in it. It's like the rocket or something is gonna fall on Earth in like 20 minutes, but the entire system was using Windows. Like, I don't know, America, NASA, Earth protection system was using Windows, which is not going to be real. It's a movie, and they're saying that the Windows is updating and it's going to take 30 minutes. So everybody on Earth is just going to die because of Microsoft. That was simple and hilarious. Yeah, this time my internet is usually good. Yeah, I do wonder what kind of system do they use for like military stuff, you know? What kind of secure system? Goes to class, take notes. Windows updating the entire class. Windows stop updating the entire class? Is it possible saying that like when the teacher needs to use the PowerPoint, the Windows just starts updating? I do remember I had classes where there's like computer problem, and those computer professors, they couldn't stop them. They have to call the technical support. Military Wing 3? What is Wing 3? If Wing 3 even a thing, there's no way they're using that. Hey, no, there's no way military is using Windows. Is that a joke? Wait, is Wing 3.1 an actual thing? Wing 3.1? 16-bit operating system? Wait, hold on. I think my grandpa used this. Yeah, you got the Minesweeper. Oh my god, this felt nostalgic. Bum 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 bum. Bum 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 bum. It's so old. I feel so old. Windows 1.3.1 runs on Microsoft MS-DOS and was among the first Windows system. Wow. During the defense of the thesis PC in room where we were doing it crash. Poor XP. Good I had my own laptop with me. Entire group was using it. Lucky them. Lucky them. Thesis defense is so very hard. Are any of you pursuing PhD right now? I'm somewhat kind of tempted of going back to school and pursue a PhD. Doing some research and do something good for humanity and find some college girls and have some good night's sleep. Dr. Nyang! Dr. Nyang! Do you need a PhD? I don't need a PhD. My whole family is against the idea of me getting a PhD, because they don't. They don't like it. They say it's a long process, and sometimes it makes people suffer. The whiteboard. I don't know. I kind of miss school, you know. If I did, I would be one of the few VTubers who have a PhD. Oh gosh. But I don't think I can do it. I don't think I have the brain power to get a PhD. Reading papers is gonna kill me. Boom. It's ultimate flex. I'm just dandy with my bachelor. What is dandy? Dandy. Start every stream with, you should know I am a doctor. Now people are not just going to, they're not going to just send me bad PCs. They're also going to check like, Cyan, I have a fever. Your doctor, cure me. You know? Would that happen? Oh yeah, I honestly do not know. Hey, thank you for becoming a member. Welcome to Nyangsa. Hello. Welcome. The only thing that annoys me is having to write papers, especially on boring topics. Boring topics? I think I kind of want to get a PhD, but I don't know what area I want to dive into. A real doctor, not just some medical thing. You'll be able to curse computer virus. Curse computer virus? Should I pursue like security and stuff? This sounds very intimidating. Next thing we know, you will be making your own hardware and writing software for it. I'm not a hardware person. I'm not a hardware person. I did remember I had a hot time with some undergraduate research. PhDs are tons of work. Expect to have no life for 4 to 7 years. Okay. Okay, I'll just be a VTuber and have a PhD of VTuber. VTuberism. Honestly though, VTuber should be an actual degree to pursue. Somebody should design a curriculum. So VTuber even has this idea of graduation. That's when they'll become a doctor. VTuberism. Oh gosh, I'll be their security teacher. Tell them to set up 2-factor authentication and password manager. University, we need a book class. Oh god, that'd be super cute. We'll start with Loop's history from its beginning to end. Okay, that was a lot of joking. Limitation of the cacher implementation. Caching values is generally useful behavior that we want to use in other parts of our code with different closures. However, there are two problems with current implementation of cacher that would make reusing it in different contexts difficult. The first problem is that the cacher instance assumes it will always get the same value for parameter arc to the value method. Also, if it gets a different value, it's going to just remember the first value. So with some hash map, it's going to solve that problem. And current cacher only accept closure that takes one parameter of type unsigned 33 and return an unsigned 33. We might want to cache the result of closure that take a string slice and return a size value. What? You recommend PhD? Oh, well, it's real pain. You start to appreciate simple things like sleep and appetite and having hair. Oh, that sounds like that sounds horrible. What's a sleep? People don't know sleep now. I think being a content creator should be something more serious. More serious than PhD? Capturing environment with closures. What is that? In the workout generator example, we only discuss closure as inline anomalous functions. However, closures have an additional capability that functions don't have. They can capture their environment and access variables from the scope in which they are defined. What is this example? What do we have here? Function main at x equals to 4 at equal to x equals c equals to x at y equals 4 assert equal to x. So does y equal to x? Wait, what? We have a few PhDs actually. I'm on 5th years of my PhD, running yet experiment on my laptop in hopes it produce publishable result. Ganbare! It's gonna be publishable, and you'll be doctor one day. Don't lose hope. It's a 5th year of PhD. You have come very far away. I've seen people dropping out in their first, second year, but you have survived those, so you are the real hero. Keep it going. Oh yeah. Equal to x. So equal to x takes a value and check if it's equal to x. So this should run. This should run just fine. Yeah. Even x is not one of the parameters of equal to x, the equal to x closure is allowed to use x variable as defined in the same scope that equal to x is defined with. So this doesn't have to be declared in the argument. It can be directly accessed from here. With functions, they'll start to question, where is the x? Like this. So it's questioning, can capture dynamic environment in a function item. So you cannot capture this. So closure is quite useful in this sense. The compiler even reminds us that this only works with closures. When closure captures a value from its environment, they use the memory to store the values for use in the closure body. The use of memory is overhead that we don't want to pay in more common cases, where we want to execute code that doesn't capture its environment. Because functions are never allowed to capture their environment, defining and using functions will never incur this overhead. Closures can capture values from their environment in 3 ways, which directly map to the 3 ways a function can take a parameter. Taking ownership, borrowing immutably, and borrowing immutably. Oh. These are encoded in this function trace as follows. Fun once consumes the variable it captures from its enclosing scope. known as the enclosure's environment. To consume the captured variables, the closure must take ownership of these variables and move them into the closure when it's defined. The once part of the name represents the fact that the closure can take the ownership of the same variables more than once, so it can be only called once. Func mute can change environment because it mutably borrows value. Function borrows value from the environment immutably. When you create a closure, Rust infers which trait to be used based on how the closure used the trait from the environment. All closures implement func once because they can all be called at least once. Closures that don't move the captured variables also implement func mute. And closures that don't need mutable access to the captured variable also implement function. Equal to x, borrow the x, immutably. It has the function trait because the body of the closure only needs to read a value in x. It doesn't mutate it. It doesn't mutate it. A good discussion. What happened in the chat? Are you going to hack me? Hack yeah. Welcome, Jubilant Love. I legit have a professor tell me that every time she sees me, I got shorter hair. Did you? Do you go to a haircut frequently? You know exorcism? There are some pretty cool Rust exercises here. Is it true? I've been looking for them. I've been trying to take the Rust class in educative as a side exercise. It's free? What? They're even for bash? That's so cool. Oh my god. It's free? There's like easy medium on the coding practices. This looks fun. I'm going to bookmark this and maybe do that one day. This looks fun. Thank you for recommending it. Hello, Suck Monkey. Welcome. Exorcism is awesome. You guys use this? What other websites do you guys recommend? This is so cute. This is so cool. They're hiring too? I did them? Nice. Nice. I mean, reading the documentation helps me understand the small details, but I do want to jump into some exercise. That would be fun. Nice. Nice. Thanks for recommending it. What is move? If you want to force the closure to take ownership of the values it uses in the environment, you can use the move keyword before the parameter list. This technique is mostly useful when passing a closure to a new thread to move data so it's owned by a new thread. Move closures may still implement func or func mute, even though they capture variables by move. This is because the traits implemented by a closure tab are determined by what closure does with the capture values, not how it captures them. The move keyword only specifies the later. We'll have more examples of move closures in chapter 16 when we talk about concurrency. But now, here is the code for what is this? What is this? How did it move it? Oh, it moved it! It has the move keyword. Capture a closure's environment by value. So we have a vector of 1, 2, 3. And then we capture its environment. And print can't use X here. And it's gonna have an arrow. Value borrow here after move. The X value is moved into the closure when the closure is defined. So when the closure is defined, the X is moved into the closure. And the closure has the ownership of X. So the main is not allowed to use X anymore. So if we delete this, it should be fine. Yup. That's so cool. You guys use move a lot? Most of the time when specifying one of the function trait bounds, you can start with function and the compiler will tell you if you need func or func once based on what happens on the closure body. To illustrate situations where closures that can capture environment as useful as function parameters, let's move on to our next topic, iterators. Okay, we're talking iterators. Processing a series of items with iterators. The iterator pattern allows you to perform some tasks on a sequence of items in turn. An iterator is responsible for the logic of iterating over each item and determining when the sequence has finished. When you use iterators, you don't have to re-implement the logic yourself. In Rust, iterators are lazy, meaning they have no effect until you call methods that consume the iterators to use it up. For example, the code creates an iterator over the items, and the code itself doesn't do anything useful. When I first heard a coding language can be lazy, I was like, what does it mean? But it's just a way of evaluation. It only evaluates when it needs to. So that's lazy. I don't know. I don't know you can treat languages like a human. Just calling them lazy. Once we have created an iterator, we can use it in a variety of ways. So we can use it in a for loop like this. I'm forgetting Rust syntax already. I've been writing a bunch of Python recently, and I'm just adding column everywhere. So vector 1 is a vec of 1, 2, 3. I've tried learning Rust multiple times, but the Rust analyzer takes too many resources and it's too slow, and other options just don't work well at all. Oh no! Sorry to hear that. Posey the Dirk. Is running Rust slow? Does it take a lot of resource with like just normal programs? At the iterator, equals to return this vector into our iterator, and then for value in iter, incline but well, I go wrong. Yup, iterate. Iterate. Iterator trait and next method. All iterators implement a trait named Iterator that is defined in standard library. The definition of the trait looks like this. So we have a type of item. We have, actually, what is this? Type item, function next, new self, option self item. So we're defining an associated type with the trait. Implementing the iterator trait requires you also define an item type, and this item type used in the return type of the next is used in the return type of the next method. The item type will be the type returned from the iterator. The iterator trait only requires implementers to define one method, the next method, which returns one item of the iterator at a time, wrapped in sum, and when iteration is over, return none. So the next method return one of the item of the iterator wrapped in sum, and eventually, when there's nothing left, it will return none. We can call the next method on iterators directly. So we have those, and instead of looping it over, assert equal, and take this iterator call next. And it gives us a sum. But why is it in a reference? Oh, there's no for. Eventually, it's none. What's the problem? It needs to be immutable. Oh yeah, it's equals to 1, 2, 3, no. We need to make this immutable because calling the next method of the iterator change the internal state that the iterator uses to keep track of where it is in the sequence. This code consume or use up the iterator. The values we get from the calls are immutable reference to the values in the vector. That's why we got this ampersand. The it method produces an iterator over immutable reference. If we want to create an iterator that takes ownership of v1 and return our own values, we can call into iter instead of iter. you, Kaijin. Welcome. And welcome, Nikkei. Hello. Thank you for coming. Wait, so it's saying if I do Intuiter, then it's not just a reference. It's the actual stuff. Nice. Method that consumes the iterator. Iterator trait has a number of different methods with default implementation provided by standard library. You can find out about these methods by looking at the standard library API documentation for the iterator trait. Some of these methods call the next method in their definition, which is why you are required to implement the next method when implementing the iterator trait. Methods that call the next are called consuming adapters. Oh, because it's eating up? Because calling them use up the iterator. One example is the sum method, which takes the ownership of the iterator and iterates through the item by repeatedly calling next, thus consuming the iterator. As it iterates through, it adds each item to a running total and returns the total when the iteration is complete. Oh, so we got a sum method. This is good news. We got some easy stuff to use. So let total equals to v1 iter dot. There's so many. Oh, any clone count. The count should return 3. Total 3. What? Oh, this is unnecessary. Yeah. And if I do sum, at 6. Oh, total needs a type. Is that total? Hello, Jordan. Welcome. Nice. Methods that produce other iterators. Other methods defined in iterator trait, known as iterator adapters, allow you to change iterator into different kinds of iterators. You can chain multiple calls to iterator adapters to perform complex action in a readable way. But because all iterators are lazy, you have to call one of the consuming adapter methods to get results from calls to iterator adapters. Oh, I'm seeing it uses the iterator with a closure. This is dope. This feels functional and powerful. Is functional language called a functional language because it's highly functional? It's like really useful. Oh. Okay. What's going on? Use of a moved value is here. It's being moved. Functional programming is I'm tempted to say paradigm again. Paradigm. Is that how you say it? Paradigm? I learned. Yo, you fun. Hello, welcome. Paradigm. No, it's not paradigm. Oh, paradigm. It's paradigm. Okay. I think one day I'll leak my human identity by saying paradigm in like a meeting or something. And they'll be like, "Are you Cyan?" Because the only other person I know who can pronounce it is like Cyan. This is so identifiable. Paradigm. Okay, paradigm. Okay. Okay. What does it actually mean? I think it means like a... Yeah, what does it actually mean? Like a practice. A typical example or pattern or something, a model. Paradigm. A model. Sexy. Konnichiwa, kawaii. Thank you, kawaii. Dox yourself by mispronouncing. Oh gosh. No, don't dox me. Oh yes, I'm encountering this. I'm like, what should I do? To fix this and consume the iterator, we'll use the collect method. We need to consume the iterator by calling the next or calling this collect. Yes? What's the problem now, my dear analyzer? We have our dear iterator, and we have a map. Okay, what's the problem now? Annotation. Whack. You don't like whack? How dare you? In French, it's basically paradigm, so my dad ass through. No, it was the same in English lemma. Wait. Paradigm. Oh. So I pronounce it in French way. I pronounce it in French way. Oh, I'm a romantic Cyan. As paradigm is correct in French, I should migrate there. Paradigm is like one of those vague sociology terms like trend or meme. Oh god. A way of programming that focuses on making full functions. Takes arguments and only work on them to return something. And use close to state. Use close to states and variables. Programming paradigms are a way to classify programming languages based on their features. Imperative, logical, functional, object-oriented. Oh! So when you talk about paradigms, you're talking about imperative, logical, functional, object-oriented. Oh, that's what it means. Slap me on the face if I forget it next time. Welcome, Rocher. Hello. What has an underscore? Exactly. Oh, okay. Looks like it's working. Let's see if I have 346. Oh, it's 234. Yeah. You can say you speak French now, Lamau. Yeah. Bonjour, everyone. I am Paradigm. Dr. Neon every day. Da. 私は Dr. Neon ですだ. OP focus on classes and that jazz, while functional is well functional. Afnia. Yeah. Imagine Pokemon. It's nothing like that. It's even Pokemon? What is chat doing? Ruby is object oriented. I forgot most of it. Salute Kawa? We're turning this into a language class. Hello everybody. Salute Kawa. Nani? That's hello. Salute Kala. Wait, what? That's French? I thought you only say bonjour. Nihongo ga wa nasemasu ka? Nihongo ga wa nasemasu ka? What does it mean? Can you speak? Hanasemasu ka? Hanaseyo. Iyo. Nihongo oishii. It means hey in French. I'm being made into a world citizen. This is dope. Okay, let's capture the environment. Let's capture the environment with closure. Hello Takawa is like, hey, how are you? Oh, Ine. How do I say? How do I say? I'm fine, thank you. 日本語おいしい。おいしいよ。Everything is おいしい。Okay. We'll introduce iterators. Oh, now we can use filter. Everybody loves filter. Oh my god, this is a long one. What is this? We have a shoe of size and style. And we have shoes inside. Ben messy. Ben messy. Ben messy. Shoes into filter. Size equals to shoe size collect. Oh. So here, all the shoes only have one size. Only the ones that match. Oh, closure is used for filter. This is like the lambda function. Soka. They're even tests. Filter by size. Shoe says shoe. That in my size equals to 10. So we have 2 that matches it. Nice. Oh, what did I do? Oh, where did the main? Oh, it's not supposed to have a main. It's cargo test. But yeah, works. Creating our own iterator with iterator trait. We can create our own iterator. We can create iterators from other collection types in standard library, such as HashMap. You can also create iterator that do anything you want by implementing the iterator trait on your own types. As previously mentioned, the only method you are required to provide a definition for is the next method. Once you have done that, you can use all other methods that have default implementation provided by iterator trait. Let's create an iterator that will only ever come from 1 to 5. First, we'll create a struct to hold some values. Then we'll make this struct into an iterator by implementing the iterator trait and using the values in implementation. Okay? We're gonna have a struct of counter. Count is an unsigned integer 32. And implement counter. Counter has a new method that returns a counter, and it initializes a counter with a count equals to 0. Okay? Oh! And you can implement the iterator. It wants a main function. Okay. It just really wants a main function. And we can implement a iterator for counter. And we implement the type. We say the type is gonna be use32 and function next takes a mutable of self and returns a optional of item and if self.count is less than 5 we add 1 to self.count and return count and else return none. And that is our custom iterator. Terraform AWS Docker. Do people actually like those? I think some people do. Ansible. All those infrastructure stuff. Making the code work. To me, I think the DevOps are the most. They do the heavy work. Very respectable. Iterators. And I can use it. So create a counter equals to counter new, and let's just call it. And the cargo run. Nice. The counter works. The counter works. Yeah, the cat is here. Oh. Using other iterator trait method. Oh my god, my cat. Hello, baby. Hello. We implemented iterator trait by defining the next method. So, we can now use any iterator trait method default implementation as defined in the standard library, because they all use the next method functionality. Oh, so we can do all this fancy stuff? Let's try. The cat is alive. Why is the cat alive? And why is it in underscore? Oh no, stop. The cat smashed the keyboard. Hello! Get on my feet. Ugh. Sit. You're annoying. Why are you purring? Is cat still hungry? I think my days at night has gone into feeding my cat. I don't think he's hungry. He just wants someone to cuddle. He fought with my other cat today. And he's probably tired. Hungry for human flesh. What? My cat is a human eating animal. We are weird. Oh my god. Oh. You know, at this point, I don't even mind if my cat scratch my sofa. stand on my sofa, the back of the sofa, and use it as a scratch pad. Oh my god. Thank you for subscribing. Welcome to Nyangstar. Okay. So, what are we doing? We're calculating a weird sum. That sum equals to counter new. We can zip counter new zip 1. What does this do? It zip with a new counter that skipped 1. What does skip do? Skip the first n elements. So it's like zipping 1 to 2 and zipping 2 to 3. A map? Oh, it's doing a... So we're calculating 1 times 2. And filter equals to 0 and sum it up. And we say equals to 18. Does it equal to 18? It does. It does equal to 18. How? What do we have? We have like 1, 2. Oh, I'm so Python. Wait. What? Where are we? Okay. What do we have? We have 1, 2, 3, 4. No. We have 2, 3, 4, 4, 5. And then we map them together equals to 2, 2, 6, 12, and 20. And anything that can be divisible by 3. That's those two, and you plus them together, that's 18. That's 18. We got an 18. This high level function for iterators. That's pretty nice. Okay, next one. Oh. I don't know where my IO project is. Nice. We're spamming nice in the chat. This is good. This feels nice. Where's my project? I have a my project. Is that my project? I have my project. Project. Which one is my project? I'm not a dog. I'm not a dog. Stop. Other culture. Which one is my... Oh, this is my project. My mini grip. It doesn't even have a project in it. Okay. Going back to this project. Pork jack? What is a pork jack? Nanio. Okay. Someone's hungry. I am a bit hungry. I went to get some tacos today. Hi. My cat has a pair of clean ears. I'm very proud. Hungry for some pork jack? What is a pork jack? What is a pork jack? Okay, so review our grab project we did last week. What did we do? We have a main function in the main file. It takes arguments from the input and we create a config out of it and handles the arrow, and we're searching for a query in a file name and run it. And in the library, we have defined the config with query and file name. And in the function, we have a new function that takes string into a config. And then in the run, we search if the given query is in the content. Yup. So, how do we want to improve this? Oh, we were cloning the arguments. It almost sounds like we can use an iterator for getting a new comment. It's args an iterator. For the time we clone those because we have a slice with string elements in the args, but the new function doesn't own args. To return ownership of a config instance, we have to clone the values from query and file name fields of the config, so the config instance can own its values. Have a good sleep. Thank you for coming, Melancholia. Enjoy your night. What happened here? So in the main file, it looks like this. And now we're removing this and changing this into args directly. It has a problem right now. This returns an iterator just as we thought. So here we're going to handle an iterator in the config when we create a new instance. So it's a mutable argument. With the type of int args. Ah, so then we can just call next. Initially, we have args next because the first argument is not what we want, and then we have that query equals to match args.next. Because we're going to unwrap the sum. Arg or none, return error, didn't get a query string. Okay. And let's copy this over. To the file name. And here I change it into file name. Good. Now we have the file name, we have the query. And in the search function, which we are going to search a query in a file name, what do we do? Oh, I think we can make it simpler by, using filter. Using filter. So the contents going to lines. And we're going to filter, and then we put the closure in for the filter function. Filter or whatever, the closure defines how do we want to filter it. So the lines with the query will be kept. And we return the lines. Iterators are nice. Functional programming is amazing. Lastly, they're going to talk about the performance of loops versus iterators. Is it the same? Or is it different? To determine whether to use loops or iterators, you need to know which implementation is faster. The version of search function with an explicit for loop or the version with iterators. We ran a benchmark by loading the entire contents of Adventures of Sherlock Holmes by Sir Arthur Conan Doyle into a string and looking for the word D in the contents. Here are the results of the benchmark on the version of search using the for loop and the version using iterators. That looks quite similar. The iterator is slightly faster. Yeah? The author from whom the anime Conan took the name. Yeah, I was like, It's that detective little boy. Yeah, the name was stolen. The Iterator version was slightly faster. We won't explain the benchmark code here, because the point is not to prove that the two versions are equivalent, but to get a general sense of how these two implementations compare performance-wise. For a more comprehensive benchmark, you should check various texts of various sizes as contents, different words and words of different lengths as query, and all kinds of variations. The point is, iterators, although a high-level abstraction, get compiled down to roughly the same code as if written the low-level code yourself. Iterators are one of Rust's zero-cost abstractions. This is like the selling point. It's like I can imagine Rust having a conference and be like, we have zero-cost abstractions. This is so cool. By which we mean using the abstraction imposes no additional runtime overhead. This is analogous to how Barjane Strostrup, the original designer and the implementer of C++, defines zero overhead in foundations of C++. I need to pronounce his name right because he seems to be really big. Strawstrop. Brianna Strawstrop. Brianna Strumpshop. I guess that's how you say it in the language. American. It says Brianna Strawstrop in Google. Barn. Brianna Strawstrop. Okay. The amazing designer of C++. Brianna Strawstrup. In general, C++ implementation obey zero overhead principle. When you don't use, you don't pay for, and further, when you do use, you couldn't hand code any better. As another example, the following code is taken from an audio decoder. The decoder algorithm uses linear prediction mathematical operation to estimate further values based on a linear function of the previous samples. This code uses an iterator chain to do some math on three variables in scope: a buffer slice of data, an array size of two coefficients, and an amount by which to shift data in QLP shift. We have declared the variables with this example, but not given them any values. Although this code doesn't have much meaning outside of the context, it's still a concise, real-world example of how Rust translates high-level ideas to low-level code. Looks simple. Like it's a hard operation, but it's a nice translation. To calculate the value of prediction, the code iterates through each of the 12 values in coefficients and uses the zip method to pair the coefficient values with the previous 12 values in buffer. Then for each pair, we multiply the values together, sum of the result, and shift a bit. Calculations in applications like audio decoder often prioritize performance most highly. Here, we're creating an iterator using two adapters and consuming the value. What assembly code would this Rust code compile to? Well, as of this writing, it compiles down to the same assembly with the write by hand. There's no loop at all corresponding to iteration over values in coefficients. Rust knows that there are 12 iterations, so it unrolls the loop. Unrolling is an optimization that removes overhead of the loop controlling code, and instead of generate repetitive code for each iteration of the loop. All of the coefficients get stored in registers, which means accessing the values is very fast. There are no bounce checks in the array's access at runtime. All these optimizations that Rust is able to apply make the resulting code extremely efficient. Now that you know this, you can use iterators and closures without fear. They make code seem like it's higher level, but it doesn't impose a runtime performance penalty for doing so. Nice! We've done talking about closures and iterators. It's been fun! It's been fun just putting closures into all these functions and make the high level code looks awesome. Closures and iterators of Rust features inspired by functional programming languages Iterators. They contribute to Rust's capability to clearly express high-level ideas at low-level performance. The implementations of the closures and iterators are such that runtime performance is not affected. This is part of Rust's goal to strive to provide zero-cost abstractions. Now that we have improved the expressiveness of our IO project, let's look at some more features of Cargo that will help us share the project with the world, which is gonna be on Friday. I'm going to continue the chapters on Friday. It's been 2.5 hours. Thank you guys for coming. That's the end of the stream today. We'll learn about closures and iterators. I get to appreciate more on using iterators and all those reducing functions. I just like map reduce. I remember using some of them in data science classes. It's nice to know there's not much performance penalty for using them. Yeah, without fear. Alright, return for the stream on Friday. And I have a Minecraft stream on Saturday. And that's about it for this week. So yeah, see you guys on Friday. Thank you for watching. Bye bye. Thank you Batomi. Thank you Zoe. Thank you Ifan. Thank you Zisha. Take care. 谢谢哈皮呀，拜拜。Thank you Kiranas of Horizon. Thank you Black Song. See you guys.